My name's Matthew Knight. I work for a company called Siemens Energy, and I've been asked to just mention a little bit about Siemens Energy. You may or may not know that we're actually a completely new company. During the pandemic, we carved out and spun off all of the energy interests of the former Siemens company. So we are now a totally separate company, just with a confusingly similar name. And we are an integrated energy technology company, which means that we make a whole range of different things that convert energy, store energy, transport energy, but we offer solutions that put those things together. So the energy transition is absolutely the heart of everything that we're about as a company. And energy is often taken for granted. I like this little image here. It just reminds me of my own sort of weak and flabby body, and the fact that the amount of electricity that most of us use on average is about 5 times what we could actually produce if we sat on a bike and pedaled. And in the winter, the amount of heat energy that we each use is probably 20 times what we could do through our own efforts. So our modern world is completely dependent on abundant energy that allows us to do much more than we could physically do as weak human beings. And when you look around the world, the numbers are absolutely staggering. Every day, the world burns 100 million barrels of oil, and in energy terms, a similar amount of natural gas and of coal. So we've got 300 million barrels worth of fossil fuel that is just being burnt every day to provide all of that energy for all of us. And the consequence of that is horrendous for the planet. We are destroying the ecosystem that we depend on for our survival, and we have to do something about that. And that means that all of that fossil fuel and the systems that deliver it and the economies that depend on producing it, all of that has to be completely replaced by something every bit as big, but sustainable and reaching more people and with a higher standard of living. And we have to do all of that in less than the next 30 years, by the middle of the century. And that's the energy transition. And that's the backdrop for the rest of all of our working lives for those of us in the energy industry. Well, closer to home, as Alok Sharma, who was the COP26 president, said last year, the time for making policy has finished, the time for delivery is overdue. And the UK now has quite a comprehensive set of policies that will, if they are able to deliver, will get us to net zero by 2050 across the whole economy. And crucially, the electricity system has to come first. And the target is that electricity will be net zero by 2035. So it's only a dozen years away. And the British Energy Security Strategy, which was mentioned just now, that came out in April, increased the short-term target for things like offshore wind and signaled that, yes, we really are going for this rapid transition, this rapid decarbonisation of our electricity system. And that's what I want to talk about in this session. And I just want to start by looking at the renewable side of that. Where are we going to get the extra clean electricity from? And the backbone of that, as was mentioned by Paul, is going to be offshore wind. So the new target is for 50 gigawatts of offshore wind by 2030. So in 8 years' time, we need 4 times as much offshore wind as we have operating today. But it took us 20 years to get to where we are now. It's worth looking at how that happened. So the first UK offshore wind farm was Blythe in 2000. It was just a couple of turbines a little way outside the harbour wall. It didn't last for very long. The cables got damaged by the tide, but that was the UK's first experiment in offshore wind. And it was followed only 3 years later by the first proper wind farms, North Hoyle being an example, close to shore, substation on the shore, 33 kV export cables, and North Oil was 60 megawatts, which you could do today with about 5 offshore wind turbines. But even while those early projects were happening, we started thinking about how we could build larger projects further out to sea with high voltage grid connections. And I was lucky enough to be part of that industry. And around about 2006, I noticed that nobody had an image of what a grid connection looked like. So I sat here in the shed that I'm talking to you from now. I made that little sketch, which somebody turned into a graphic. And for a while, that was the only image that anybody in this industry had of what an offshore grid connection was going to look like. But within 3 years, we started to build them, and somebody conveniently took this photograph from nearly the same angle. The industry's come a long way since then. We've built a lot more substations and a lot more wind farms. And I'm particularly pleased with this image here, which shows not 1, but 5 substations under construction at the same time in the same shipyard for 2 different projects, 2 for Triton Knoll and 3 for Moray East. And as you can see, the scale of Moray East means that we're now into gigawatt scale offshore wind farms. So while we were building the wind farms, we were also building the industry that's going to deliver at the scale that we need to do these things. The substations got smaller and cheaper, and we built more of them. And we learned lessons, and a lot of new people joined the industry. There was a report earlier this week that shows 31,000 people now work in the British offshore wind industry. And that number is expected to rise to 100,000 by 2030. So in that context, the idea of doing 4 times as much in half the time as we've done already to hit that 2030 target begins to sound a little more achievable. And it depends on supply chains for everything. And I was lucky enough that the best day of my working life was the day that I was the face of Siemens Energy when we announced that we were going to open the blade factory in Hull to make wind turbine blades for offshore wind farms. If you ever get the chance to go to a city and announce 1,000 jobs, I can really recommend it. But making investments like that required confidence that there was going to be a pipeline of work. And that involved a strong collaboration between government, between our customers and Siemens Energy, or now Siemens Gamesa, in order to make that investment happen. And similar kinds of things have to happen in every part of the supply chain. But there are investments that pay off. This is a photograph from last month showing that we're now doubling the size of that factory so that it can manufacture even larger blades and support the growth of the offshore wind industry. So I think it's believable that we can deliver the extra offshore wind, that part of the net zero by 2035. But that's only a small part of decarbonising the whole economy. These are some numbers from the Committee on Climate Change from a couple of years ago. And you can see that offshore wind, yes, we need to go from 12 gigawatts to 50 this decade, and then double that again by the end of the next decade. Sorry, I'll just that. We also need to double the size of our electricity system, and we need to invent whole new industries of a similar scale for carbon capture and storage and hydrogen production. And we need to do massive things for domestic heating. And all of those industries will need their supply chains, and they'll all need to grow in parallel at the same time. And that's what the energy transition is all about. Well, we've spoken about renewables, and one thing we know is that the wind doesn't blow all the time. And as Paul said, we're going to need a combination of storage and dispatchable generation to be able to manage a system that's dominated by wind. And storage comes in a range of different technologies, pumped hydro like this, but also hot rocks or compressed air energy storage, and a whole range of chemical vectors, things like hydrogen and ammonia. And we're going to need all of them, and we're going to need them at scale. And we're also going to need dispatchable generation. And there are 3 basic ways that you can deliver dispatchable electricity generation. If you start with a fossil fuel, you either have to clean up the emissions on the back end of your generator, or you can treat the fuel before you put it into the generator, capture the carbon dioxide, and make a fuel like hydrogen or hydrogen-based synthetic fuel. Or you can avoid the fossil fuel altogether, and you can use even more of that renewable electricity and water to make hydrogen and hydrogen-based fuels and put that through gas turbines. So we're moving away from the idea that we were storing energy as lumps of coal or gas in reservoirs into a world where we have to make and then store and then convert the energy when we need it. The first two of those ways involve carbon capture and storage, and carbon capture and storage is a really bad idea. Carbon capture and storage is the energy equivalent of landfill. We're not fixing the problem, we're just burying it. And carbon capture and storage is absolutely essential if the UK is going to get to net zero. The Committee on Climate Change have said we just cannot deliver a net zero economy without large-scale carbon capture and storage. But it's not a trivial thing. It comes in big projects and it involves a lot of energy. If you want to put carbon capture on the exhaust of a power station, you end up using somewhere between 5 and 10% of the electricity generated by that power station just to operate the capture plant, to capture about 90% of the carbon dioxide. And then you've got to bury that carbon, lock it away forever. And if you can visualize trying to push a beach ball to the bottom of a swimming pool, that's the kind of thing that is involved in putting carbon dioxide at such high pressure that it might almost be liquid, a kilometre or more below the seabed. Excuse me. But the UK has to do carbon capture and storage, and we are going to do it. And the first two carbon stores have been selected, one that will serve the Mersey area and one that will serve Teesside and the Humber. And there are 47 capture projects going into the first round of funding that will be putting carbon into those stores. And some of you might have seen that yesterday there was a new round of carbon storage was announced. So we're going to be burying carbon dioxide, and we're going to be using some of that to make large quantities of hydrogen. And we will need large quantities of hydrogen. This is a 9000 HL, which is a large gas turbine. We've just commissioned one at Keadby 2, which is an SSE power station on the banks of the River Humber. Keadby is the most efficient power station in Europe, and it runs on natural gas. If we wanted to run it on hydrogen, we would need about 50 tons of hydrogen every hour. And 50 tons of hydrogen, if you filled one of the salt caverns on Teesside with hydrogen, you'd be able to run this gas turbine for about 3/4 of a day. And that turbine is capable of producing maybe 1% of the electricity that we're going to be requiring in our net zero electricity system by the middle of the next decade. So you can see we're going to need a lot of hydrogen and a lot of dispatchable power. We can make hydrogen in two different ways, and they're colloquially called blue hydrogen and green hydrogen. And although the product is similar, it's low carbon hydrogen, really they're two almost completely separate industries. Blue hydrogen is much more like the nuclear industry, whereas green hydrogen is more like the solar industry. Blue hydrogen comes in large autothermal reformers, big chemical plants. It needs to be attached to a carbon store, and it produces in bulk and is going to be located very close to where it's needed. Whereas electrolyzers these days are about 1 megawatt, but they're rising, and we'll see those get larger, and they can be spread all over the place, and they can be built relatively quickly. And that's important because the green hydrogen industry needs to grow by about 4 orders of magnitude this decade. So it's not 4 times, that's 4 orders of magnitude, 10,000 times. But we think we can do it. The scale of the electrolyzers that we make in Siemens Energy has gone up by a factor of 10 every 4 or 5 years. Our production capacity last year was 250 megawatts. By 2025, it's going to be 3 gigawatts a year. And there's a whole range of other things alongside the electrolyzers, compressors, water treatment, and the electrical infrastructure that goes with that also needs to ramp up as well. And we're starting to see larger and larger projects. I've deliberately chosen projects that are not in the UK for this slide, but there are similar size projects that we're talking to people about in the UK. So you'll see on the left there, that was one we delivered last year that was 8.5 megawatts. Most of the projects that we're delivering this year are in the sort of 20 megawatt range. We are working on 50 megawatt projects, and just a few weeks ago, we announced a 200 megawatt project in France. So the projects are scaling up. Now, I've hit you with a lot of different technologies there, and often the advocates of one particular technology tend to talk about it like a silver bullet, or the press like to set one technology against another. So, will it be green hydrogen or blue hydrogen? Will it be hydrogen or heat pumps? Will it be nuclear or carbon capture and storage? If we're going to deliver a net zero electricity system by 2035 and a net zero economy by 2050, we're going to have to do all of them at scale, and we need to start very quickly. Now, if that sounds too big and too scary, and maybe you can't see how it applies to you, here's a little hierarchy that you can use when you're looking at your own business and your own line of work. How can you contribute to meeting these targets? And the first thing to do is to stop adding to the problem. It's verging on the criminal to be building something today that you've got to decarbonize in a few years' time. So we need to start putting in things that are ready for decarbonisation, even if they're not operating at low carbon in a low carbon way today. Energy efficiency is really vital. Using less doesn't get us to net zero, but it does buy us a lot more time. What matters to the planet is the total amount of carbon dioxide and greenhouse gas that we emit. So getting our energy in a more efficient way is a really important thing that we can start doing, and in many cases we can do quite quickly and quite cheaply. We know that switching to renewable electricity is going to decarbonize our electricity system, and whatever we can, we want to transfer onto electricity. But where we can't do that, can we substitute fossil fuels with clean alternative chemical fuels, low carbon hydrogen? When we've done all of that, maybe we still need to capture some of the emissions coming out of the back end. And if you're lucky enough to live in one of the carbon industrial clusters, somebody's talking in the background, perhaps you could mute, please. If you're lucky enough to be in one of the industrial clusters, you will be able, by the end of this decade, to export carbon dioxide for burial as part of cleaning up your process. Because the energy is going to be in different places, and Paul showed us the boundaries, we're going to need to balance the system differently, and that's going to require energy storage, and it's going to require things like rotating grid stabilizers and flexible AC transmission systems. And even when we've done all of that, I heard Professor Sir David King, the UK's former climate envoy, speak to a Siemens Energy audience last week. And he said something quite powerful. We are already nudging up against 1.5 degrees of warming. And greenhouse gas that's in the atmosphere goes on warming for many, many years once it's up there. So if we want to stay below 1.5 degrees, every kilogram of carbon dioxide that we emit from now onwards, somebody is going to have to suck that back out of the atmosphere over the next 50 years or so. So we need to get into greenhouse gas removal, and whether that's removing methane from old mine shafts or whether it's carbon capture and storage, we're going to have to reverse the damage that we've done. And there's a whole load of policies that government have come up with to do all of those things, and I won't enumerate them. If all of that sounds just too scary, it's worth noting that when the conditions are right, change can happen very quickly. And I love this graph because it shows how we've switched off coal in the British electricity system. In 2012, 45% of our electricity generation came from burning coal. In 2017, we had the first day with no coal generation at all since Queen Victoria was on the throne. And as you can see by the amount of green at the bottom of the graph, in the last couple of years, there's been very little coal generation at all. So when the conditions are right, change can happen quickly. And the next change is we need to switch off the natural gas, especially for heating, but we also need to find different ways of doing dispatchable power generation that don't involve unabated burning of natural gas. So this energy transition is really just a speeded up version of a trend that's been happening for centuries. Back in 1870, if you talked about energy in Britain, energy was coal. It was used for heat and it was used for power. But it was dirty and smutty and it discoloured our buildings. And so people worked out that you could process coal to make coal gas, town gas, and that started to be delivered through pipes. And it was a cleaner version of energy. And then in the 1970s, we found a cleaner source of natural gas underneath the North Sea. And that's the thing that's powered our world for the last few years. And then in 2020, this is a smiling group of people from Worcester Bosch unveiling their new hydrogen-ready domestic boiler. So this is a trend that's been going on for a while. And if you find that trend worrying, it's maybe to do with the way you think about your job. If you think of yourself as working in the oil and gas industry, you're linking your purpose in life to a fossil fuel, to a commodity. But if you think of yourself as working in the bringing energy to people industry, that's a really noble, important thing to do that needs to go on happening for many years to come. If you're in the bringing energy to people industry, there's just one extra constraint. We just have to do that in a net zero way. So it's possible to be in the energy industry and look forward and see the very exciting opportunities that are happening with growth happening in the gaps between the old industry. Handling carbon dioxide, making and using hydrogen, energy storage. These are the things that start to couple together the historically separate sectors of oil and gas, renewables, electricity transmission. And they are spawning a whole load of new industries. And those industries require skills that are a hybrid of what came before, which means that we're going to need to learn new things and we're going to need to collaborate in different ways in order to deliver this net zero world. And if that's not a great opportunity for the rest of your working life, I don't know what is. And it's going to happen. Businesses all over the world are now committing themselves to net zero. People are investing in this stuff. And why are they doing it? They're partly doing it to save the planet. We have to do that. But they're also doing it because the legislation and the regulation is in place. They're doing it because the investors are demanding it. By 2025, over half of all of the money that's invested on this planet will be in ESG funds with strong environmental requirements on where that money goes. But lastly, the main reason why we need to do this is we are the generation that has to do it. Our children and our grandchildren will demand that we do it. We need to step up and we need to transform our energy system, and we need to do it quickly because we have fewer than 1 billion seconds left to deliver net zero. Thank you.
Thank you, Matthew. That was both thoughtful, insightful, and it was. Thank you. We do have a question from the audience. Martin says, what is your view on geothermal? Could this unlock carbon capture and storage?
Geothermal. So there's sort of more traditional geothermal, where you tend to use a fluid that's sort of water-based and hot rocks, and that's quite specific to the location. You need hot rocks close to the surface. And then there's another form of geothermal where you actually use carbon dioxide as the working fluid, and you send it round and round. And that looks like it has potential because it could operate in many more regions of the world, and it would be a place to put the carbon dioxide. Once you've filled it with carbon dioxide, it doesn't go on disposing it, but it is part of the mix. I think, though, that one is at a very early stage, and the message that I would particularly for policymakers, is don't rely on a future silver bullet. We're going to have to decarbonize the electricity system of this country using the technologies that we already have today. The ones that I've mentioned, we just have to scale them up quite quickly. There will be new technologies, and they'll be great, and they'll come along, and they will help us maintain a sustainable system beyond 2030, 2040, 2050. But typically it takes 20 years for something to go from the lab to getting deployed at scale. It took us 20 years to get to scale in offshore wind. We don't have the time to hang around for silver bullets. So we have to start doing what we can do now.
Yeah. There is another question from John Hanson, who says, town gas was 50% H2. Is that better than methane?
Well, the way it was made means that it wasn't better than methane. Coal is hydrocarbon. So's methane. A lot of carbon and a lot of hydrogen. When you burn it, natural gas is cleaner than coal. So typically, at the point of combustion, coal is 4 times more carbon damaging than natural gas. But the dirty secret of methane is methane itself is a greenhouse gas. It's 85 times more potent than carbon dioxide. For the first 20 years, it's up in the atmosphere. And fugitive methane emissions between the well and consumption, and then slippage through whatever you're burning it in, can make burning methane every bit as environmentally damaging as coal. So we need to get off both of them. We need to move away from fossil fuels. I suppose the good thing about town gas having had a high hydrogen content is that a lot of the equipment on the gas network can contain hydrogen. The plastic pipe replacement program since the 1980s means that a lot of our networks are capable of taking hydrogen. But if you've ever seen something called the Michael Liebreich ladder that shows where hydrogen has more valuable and less valuable uses, the least valuable thing to do with hydrogen is just burn it for heating. There are a lot of other things that you should be using it for first.
Perfect. Thank you so much for that. I know we're out of time now. I really appreciate it.